Hello and welcome. Today we're exploring molecular representations for machine learning in chemistry. Here's the challenge. Molecules are complex three-dimensional structures with atoms, bonds, and dynamic properties. But machine learning models need numbers, vectors, and matrices. How do we bridge this gap? That's where molecular representations come in. They translate structural and chemical information into formats that algorithms can process. Why does this matter? Because your representation choice directly impacts model performance. Choose wisely and you unlock powerful predictions for drug discovery and material science. Today, we'll cover molecular fingerprints, descriptors, 2D and 3D representations, and modern learned approaches. Molecular fingerprints. Molecular fingerprints encode molecules as bit vectors, like barcodes, where each position indicates presence or absence of structural features. Key types include structural keys, like MACCS keys, use 166 predefined patterns, such as contains benzene ring or has carbonyl group. They're interpretable but limited by predefined rules. Circular fingerprints, or ECFPs, algorithmically explore neighborhoods around each atom within a certain radius. ECFP4 is most common, capturing local environments without predefined patterns. Path-based fingerprints encode linear paths of atoms and bonds, efficiently capturing connectivity patterns. Fingerprints excel in virtual screening and similarity searching. However, they can suffer from bit collisions and don't capture 3D shape information. Molecular descriptors. While fingerprints encode pattern-based encoding, descriptors give numerical values measuring specific molecular properties. Constitutional descriptors count atoms, bonds, rings, and molecular weight. Simple but useful. Topological descriptors measure connectivity patterns through indices like the Wiener index, encoding molecular graph shape without 3D geometry. Electronic descriptors capture properties like partial charges, polarizability, and orbital energies, often requiring quantum calculations. Physicochemical descriptors encode real-world behavior, log P, polar surface area, and solubility, critical for predicting drug properties. Tools like RDK and Mordred can calculate thousands of descriptors. The advantage is interpretability, but challenges include feature selection and multicollinearity. 2D representations. 2D representations encode connectivity without three-dimensional geometry. SMILES represents molecules as text strings. Ethanol becomes CCO, simple and database-friendly. Recent work uses SMILES with language models, treating chemistry as a language problem. Selfies improves on SMILES by guaranteeing every string represents a valid molecule, crucial for generative models. Molecular graphs treat atoms as nodes and bonds as edges, with features for element type, charge, and bond order. Graph neural networks learn directly from these structures, making them extremely powerful for property prediction. 2D representations are fast since they don't require 3D conformer generation. 3D representations. Many properties depend fundamentally on three-dimensional structure. Drug target binding, for example, requires proper spatial fitting. 3D descriptors include molecular shape measures like principal moments, surface area, and volume. Pharmacophore features capture the 3D arrangement of donors, acceptors, and hydrophobic regions. 3D fingerprints, like E3SP, encodes spatial relationships between atoms. Field-based representations place molecules on 3D grids, computing electrostatic and steric properties suitable for 3D convolutional networks. The challenge is conformational flexibility. Molecules adopt multiple shapes, requiring strategies like using multiple conformers or ensemble methods. Emerging approaches. Modern deep learning enables learned representations directly from data, potentially capturing patterns that handcrafted features miss. Self-supervised learning methods like masked atom prediction train on unlabeled data, creating pre-trained encoders for fine-tuning on specific tasks. Transformer models like Kim-BERTA learn contextual SMILES embeddings for property prediction and molecule generation. Multimodal representations combine 2D, 3D, and textual information into unified embeddings. The trend moves towards learned, physically informed, transferable representations. Summary. Let's recap. Molecular representations bridge chemistry and computation. Fingerprints encode substructure patterns as bit vectors for similarity searching. Descriptors quantify interpretable molecular properties. 2D representations like graphs power modern neural networks without requiring 3D structures. 3D representations capture spatial arrangements essential for binding and reactivity. Learned representations from deep learning increasingly complement traditional approaches. 3 key takeaways. First, no single representation is universally best. Choose based on your task and data. Second, different representations capture different molecular aspects, substructures, properties, connectivity, or spatial arrangement. And third, the field evolves rapidly, with learned representations achieving remarkable results. How we represent molecules shapes what we can learn and predict, driving advances in drug discovery and materials science. Thank you for joining this exploration. Happy modeling!